project, we will simulate a self-propelled submarine motion using the dynamic mesh option. The present problem simulates the motion of a self-propelled submarine floating on the water surface by dynamic mesh method using ANSYS Fluent software. In this simulation, a computational domain considering air and water with a certain level is designed, so that a self-propelled submarine is floating on the surface of the water. In such models, the location of the cells in the grid changes due to the displacement of their adjacent boundaries over time, and therefore, to define the instantaneous grid shift, we benefit from the dynamic mesh model. Also, it should be pointed out that the VOF multiphase flow model is used to simulate two phases of air and water. The present model is designed in 3 dimensions using AutoCAD, CATIA, and ICEM softwares. The horizontal length of the submarine is 16.25 meter, and at the end of it there is a number of impellers with a diameter of 0.825 meters. Around the submarine, a cylindrical computational area is designed inside a cubic area, the set of which is placed inside a very large cube as a total computational domain. The meshing of the present model has been done using ICEM software. The mesh type is hybrid, meaning that a combination of a structured and unstructured mesh is used. Thus, meshing in areas close to the submarine hull is unstructured, and in general areas of the model is structured. Also, the element number is equal to 2,802,219. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure based since we are dealing with incompressible flows. Also, the velocity formulation is taken to be in absolute form. And as for the time study, we have selected the transient time study since we are dealing with a time progressing phenomenon. Also, in order to model the buoyancy forces, we had enabled the gravity, and its value is equal to minus 9.81 in z direction. Now under the model section, if you double click on the multiphase button in the appear window, you can see that the volume of fluid model is enabled in order to simulate the two phases of air and water. Also under the volume fraction parameter section, you can see that the implicit formulation is selected. Also, as explained in previous slide about the body forces, you can see here that we have enabled the implicit body force. Also, as was explained in the project description section, we have enabled the open channel flow, and under the number of learning phases, you can see that two phases of air and water are set to be defined and simulated. And if you click on the phases tab, you can see that air and water are defined as primary and secondary phases. In order to add a new phase, just have to click on add phase button. But you should be aware that before adding a new phase here, you should add that material in the material section, which will be explained in next slides. Also, Click on the phase interaction tab. You can see that the surface tension force modeling between the two phases of air and water are enabled, and the value for surface tension coefficient between these two phases is set to be equal to 0.072. After double-clicking on the viscose button, a new window will appear. In the appeared window, you will see that we have chosen two equations, standard K epsilon, to solve for our fluid flow. The standard K epsilon model is one of the most renowned model for solving the turbulent fluid flows, and actually two equation K epsilon model allows the determination of both a turbulent length scale and time scale by solving two separate transport equations. If you expand the fluid under the material section, you can see that two materials of air and water are defined here as our two main phases. Also, in order to add a new material, all you have to do is to right-click on fluid and then select new. In the appeared window, you either can define a new material by defining its properties yourself, or you can simply click on Fluent Database and add a new material from the available list of material from the Fluent software. Now, in order to correctly model the buoyancy forces applied on the geometry, we need to define the reference pressure location for the software. To do that, we double click on Cells and Conditions and we click on Operating Conditions button. Now, if we click on each of these air inlet boundaries, you can see that the type of these boundaries is defined to be velocity inlet. By clicking on Edit button, a new window will appear in which you can change the settings for these boundaries. In the appeared window in front of the velocity magnitude section, you have to enter the value of 1.62 meter per second. And under the phase section, if you change from mixture to water, you can see the water volume fraction is set to be 0, which means that only airflow enters this boundary. And just like the previous boundary, if you click on each of these inlet water boundaries, you can see that again the type of these boundaries is defined to be velocity inlet. By clicking on Edit button, again you can change the setting for these boundaries. In the appeared window, you can see the same settings for the air inlet boundary, with the difference that if you click on the phase section and change it from mixture to the water, you can see that the water volume fraction is set to be equal to 1, meaning that only water will enter these boundaries. And if you click on the upper part boundaries, you can see that under the Momentum tab in the appeared window, in front of the coordinate system, we have selected the Cartesian coordinate, and in front of the X velocity section, we have entered the value of 1.62. Again, if you select the phase section and click on water phase, you can see that the value of water volume fraction over these boundaries is equal to 0, meaning that only air can enter these boundaries. Now, if you click on the outlet boundaries, you can see that the face related to this boundary is divided into three sections. The upper section is related to the air outlet, and the middle and the lower section is related to the mixture of air and water outlet. If you click on the outlet boundaries related to the airflow, you can see that under the Momentum tab, the gauge pressure value is set to 0. Now, if you click on the boundaries, which are placed in the middle section and lower section of this phase,
In the appeared window, if you click on the multi-phase tab, you can see that the open channel option is enabled, and free surface level value and bottom level value are entered, as you can see in this slide. The same setting is also applied for the outlet boundary, which is placed in the lower section of our outlet face. And if you click on each of wall boundaries and then click on edit button, in the appeared window you can see that the stationary wall motion along with no slip shear condition are defined for these walls. Now if you double click on the dynamic mesh button in the appeared part, you can see we have enabled the dynamic mesh option, and under the mesh method we have enabled two options of smoothing and remeshing. By clicking on settings button, we further adjust these two options. In the appeared window under the method, you can see we have enabled the spring Laplace boundary layer. Also, the spring method is a method in which the mesh cells act just like a spring when they are pushed or pulled by the moving object. Also in this window you can see this specification for this method. Also, if you click on the remeshing tab, you can see that the local cell option is selected, and under the parameters you can see the values which indicates when the remeshing occur. Now setting these values will be explained in next slide in details. Under the options, you can see 6DOF and implicit update are enabled. By clicking on settings button, we can further change and adjust the settings related to these options. In the appeared window under the 6DOF, you can see we have enabled the write motion history, and underneath it you can enter the address where you want to save this file, which gives you the location and the changes in angle of the floating object in terms of time. In this project, since we are calculating the forces that are exerted to the floating object, in order to avoid divergence and in order to map the values of the forces on the new mesh after each remeshing interval, we have enabled the implicit update, and you can see the values for these settings in this window. Now, in order to set the settings for dynamic mesh for different zone, we click on create or edit button. In the appeared window, if you click on the moving mesh zone, you can see that the type of this zone is defined as rigid body. Also under the motion attributes tab, you can see that under the 6DOF UDF or properties, an UDF is defined, and under the 6DOF section you can see we have enabled this option. Also under the center of gravity location, we have calculated the center of gravity of our submarine using the SolidWorks software. Now in order to introduce and compile the UDF for the software, all you have to do is to click on user defined tab and then go over functions and select compiled. After clicking on the compile button in the appeared window, by clicking on add button, you can select the UDF file which will be given to you with the rest of the files, and then by clicking on build and then click on load, this UDF will be loaded for the software. And we do not need to change anything under the meshing option tab. And if you click on the solver option tab, you can see we have enabled the solution stabilization with the scale factor, as you can see in this window, in order to increase the accuracy of our solving and in order to avoid any diverging. If you click on the moving mesh zone, you can see that the type of this zone is defined to be rigid body 2, and under the motion attributes tab you can see we have applied the UDF to this zone too. Also, the center of gravity of location is, as you can see in this window, and under the 6DOF section you can see we have enabled this option, and we have also enabled the passive mode too. Now if you click the deforming mesh zone, you can see that under the meshing option tab, the remeshing and the smoothing option are defined for this zone. Also, if you can remember, in the previous slide we talked about the parameters that stipulates the remeshing process. You can see the same parameters here. By clicking on zone scale info, we will explain how to define these values correctly. In the appeared window, you can see the quality info for the manually generated mesh at the first place. Now we want the new mesh after the remeshing interval to almost have the same quality as the first mesh. So we enter the values under the parameters section as near as possible to the info which is shown in the zone scale info window. We also enter the same values in the mesh method setting window under the remeshing tab.
After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first-order upwind and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field.
In the solution control section, we change the values of under-relaxation factors for parameters like momentum, turbulent kinetic energy, or turbulent dissipation rate in order to avoid divergence and to increase the accuracy of our solution.
There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well.
If you expand the report definition section, you can see that a report is defined here. If you double click on it, in the appeared window, you can see that this report is defined to calculate the drag coefficient over the surface of our submarine. In this window, you can see that under the force vector section, the value for the x is defined as 1 since the drag force is applied on the submarine in the x direction. Also under the val zones, we have selected the moving, which represents the surface of our submarine.
After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software.
Now in this slide you can see that the water volume fraction in the domain is equal to 1, which means that we have water in our whole domain without any air. Now to make the software to understand that the half of our domain is filled with air, we have to patch this information. But before patching, we click on domain and then go over depth. In this part, we will define the separation line or the interface between two phases of air and water in our domain. To do that, we click on Adapt and then go over Refine or Coarsen. In the appeared window, you have to click on Cell Registers and then click on New. Since we had previously defined this region, we click on Manage to show the settings related to this separation line. After you selected the new, a window like this will be shown to you. In this window, under the shapes, you will have to select the hex, and under the input coordinates, you have to enter the values as you can see in this window. And then click on Save button. Now after defining this separation region, you have to click on Patch button. Under the phase, we select the water phase, and underneath it, we select the volume fraction variable, and we set this variable to be equal to 0. And under the registers to patch, we select the region 0 where we had previously defined in previous slides. After that, we click on Patch button. After the process of patching, we double click on Run Calculations button, and in the appeared window, under the parameters, we enter the values of number of time steps and time step size and max iteration per time step as you can see in this slide. After that, we click on Calculate button and the software will start the simulation process. It should only be pointed out that if you face divergence, try to first disable the dynamic mesh option and then start the simulation process and then run the problem for 1 or 2 iterations. After that, you can stop the simulation process and enable the dynamic mesh option and then continue your simulation process. In order to extract 2D contours, we first have to define a plane. To do that, we right click on Surfaces and then go over New and then select Plane. In the appeared window under the method, we select 3 points and we enter the needed value as you can see in this window. Now that we have created our plane, in order to extract 2D contour, we have to expand the graphics section and then go over contours and right click on it and then select New. In the appeared window, in order to extract the volume fraction of two phases of air and water contour, under the contours of section you have to select phases, and under the phase section, for example, select water phase. After that, under the surfaces section, we have to select our defined plane and then click on Save or Display button. In this contour, you can easily see the free surface of water and that the object is floating on the interface between two phases of air and water. In order to extract the velocity contour over this plane, all you have to do is to change the contours of section from phases to velocity. After that, just by clicking on Save or Display button, the software will show you this contour. Now in this contour, you can easily see the changes in velocity of the air and water after they pass over the floating object. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.